start with the first invited talk. If there are any questions, please use the Q&A button and we will see them and we will relay them to the speaker. Okay, and with that, it's my pleasure to introduce Iro Armeni, who's currently completing her PhD at Stanford University, where she's doing research in the intersection between civil engineering and machine vision. So she's doing a lot of very interesting things on automated semantic and operational understandings of buildings throughout their life cycle using visual data and towards establishing a seamless interaction between the physical world and its digital representation. Before she joined Stanford, she did a Master of Science in Computer Science at the Ionian University in 2013 and a Master in Engineering in Architecture and Digital Design at the University of Tokyo in 2011. Furthermore, she has a diploma in architectural engineering from the National Technical University of Athens from 2009. She got the 2017 Google PhD Fellowship on Machine Perception and the 2009 Japanese government MEXT scholarship, and soon she will join ETH based on a postdoctoral fellowship from ETH. With that, Armeni, please take it away.
Thank you, Torsten. Good morning, everyone, or good evening, wherever you are in the world. I'm talking to you from California. It's currently around 2 a.m. So I would like to talk to you about a very specific work of mine, 3D scene graph, which I presented in ECCV 2019. So before I explain details about the work, I'd like to begin with this, that we live in a physical world, but we are quickly transitioning into a hybrid one, where alongside us, we'll see a lot of virtual and augmented reality applications, robots assisting us, as well as a lot of automation happening around us. So we need to find a way to have this physical world interact with the virtual world, and specifically with a digital representation of the virtual world, a digital representation that's going to be general so that it can feed into application-specific afterwards representations. And then we also want the connection between the physical world and the digital representation to be seamless. So every time there's an update in one or the other one should be updated as well. And when we look at the two ends of this seamless interaction, from the side of the physical world, the users who are going to interact with the information, with the digital representation, are going to be humans and agents and machines. So this means, that the digital representation has to have a structure that is going to be interpretable by both humans and machines. So for example, you can do easily queries on them, or you can learn, if you're a machine, from this data in order to perform tasks. And with this, I want to start talking a little bit about the 3D scene graph work, and you'll probably see how this ties into the rest of the talk. So we have a lot of data sets in computer vision. A lot of them are about semantics, and all of them have very different ways that they can represent semantic information with image level labels, such as ImageNet, with 3D shapes, such as in ShapeNet, or with image captions, like in Coco. But there are two main questions that we should always ask when we are thinking about representing semantic information. What should the structure or the format of this information be, and where should it be grounded? Beginning with the what, with the structure of it. There we see that there are different ways to do that. For example, you can, given this image of the scene, you can represent the semantic information with an image level label. So just saying that here we have a chair. You can also add a bounding box or a segmentation mask and localize the object. Or you can use natural language captions to describe a little bit more with a little bit more freedom what exists in the scene. Such as, for example, that a dining chair is on a rug. And then we also have the work by Krishna et al., the 2D scene graph, where you can represent the scene and with the objects and attributes of them, and you can start putting connections between those attributes and elements, forming a graph. Now, what would be the grounding space? we have a lot of different paradigms, where one would be the case of grounding information, semantic information on pixels, so in the 2D world, although that has some difficulties when we have a change of the viewpoint, even a slight change in the viewpoint, then we have to re-annotate or relabel the whole image. Then we have pure 3D geometry, which, although it's a little bit more invariant than the 2D domain, still we do not have access to images which comprise a lot of the input to our neural networks these days. And finally, we have the opportunity to connect 2D and 3D information by registering images in 3D. And I'm not gonna talk about that step, which I understand a lot of you are probably interested by joining this workshop, but I would like to talk about the semantic information and how we can understand objects and how we can think about structuring our information or semantic information in a way that we can leverage it for doing better localization, for example. And with this, we proposed 3D SyncGraph, a structure that is it's inspired from the 2D SyncGraph work and is extended in the 3D space by introducing different elements, by including different elements, as well as attributes and relationships between them. But we're going to go into that in more detail right away. So the 3D SyncGraph structure has 4 layers. The first one is that of the building, where it's a node in the graph. Then we have spaces, the rooms inside each building, which are also nodes in this graph. We have the objects that consist the spaces. And then finally, the camera, so any kind of 2D image, is part of the graph, which means that we can do a lot of tasks or inference tasks or navigation tasks with the use of the 3D SyncGraph by including the camera in the graph. The elements have also attributes. So for example, we know the function of the building. We can say that the sync category of that space is a living room, that an object has this material and that texture. And of course, for the cameras, we're talking about the intrinsic and extrinsic parameters of them. We also form relationship between those nodes and those elements, otherwise we wouldn't have a graph. For example, we can query the relative volume between 2 spaces, or we can cross over layers and, for example, query if 2 objects belong to the same parent space, or whether an object is occluding another object given a specific camera. Now, we wanted to demonstrate this structure, the semantic structure, semantic data structure. And the Gibson database, which is the largest real world interior building data set, was the perfect playground for us, because it does not have semantic annotations, and given the size of it, it would be great if we could actually have that for general purposes, of course, of learning semantic tasks, but also for embodied active learning. So we provided semantic annotations on them that have to do with 3D mesh instance segmentation, with 2D panorama instance segmentation, with relationships and rich attributes such as materials, function of rooms and buildings, etc. But the question here is, when we have all this kind of rich semantic information, how can we get it? How can we build a mechanism, a method, a framework that we can acquire this semantic information from raw data? So we built a semi-automated labeling pipeline that begins with the available raw data that the Gibson database has, which is 3D mesh and registered panoramas. That gives us as an output 3D and 2D instance segmentation. And then there is a subsequent step of computing the attributes and relationships between them. There's also a step of user-in-the-loop verification, so that we can make sure that the accuracy and the performance of the automated method is improved to almost 100%. I'm going to skip. This is just about what other semi-automated methods exist, both for 2D and 3D. But what is important is that we start with a hierarchical method that begins in the 2D space and at the end reaches the 3D space. And we leverage existing 2D semantic detectors, and specifically Mascar CNN, in order to perform this task. So Mascar CNN has been trained in COCO and was directly applied on the Gibson data with no training at all or fine-tuning. And we saw that there are, although it performed very well, we saw that there are some common errors that most detectors are making, specifically on objects that are at the boundaries of an image or are very far away from the camera. So they are represented with very few pixels in the scene. And for this reason, we built two robustification mechanisms of the output of Mascar CNN. First one is the framing, and second one is the multi-view consistency. Now, when we are given a random frame and we, let's say, pass it through Mascar CNN, in this specific frame, we see that the couch was detected as a bed and the counter in the kitchen was not detected at all. But if we were to update slightly the frame, we would see that the couch is able to be detected correctly, and same for the counter in the kitchen. And what that tells us is that if we frame our objects in the center of the image and is zoomed in so that it's visible enough, but also there is context around the object, then we can have high probability in actually predicting the correct label. And the good part is that in our hands, we have panoramas, RGB panoramas, which allows us to frame however we want a rectilinear image. So we build a mechanism that is going to create a lot of rectilinear images given the panorama. And we densely sample them with the parameters that you see on the slide. We take each of these frames and we pass them through Mascar CNN. So now we have a lot of predictions about the pixels on this panorama. And since we are densely sampling, a lot of those frames are overlapping. So how can we actually disambiguate conflicting labels? Because for a pixel, we might have 10 labels as predictions, and 7 of them might be something, and 3 of them might be something else. But how can we disambiguate which one we're going to choose as the correct label? And for this, we developed a weighted voting scheme where we take into account the confidence score of Mascar CNN and the distance of the segment from the center of the image. And here you can see on the right the final result of performing this step on the panorama on the left side of the slide. Now we see that if we are just the previous step, which is the framing step, does not give us 100% correct, accurate results. We still have some issues that might be because for example, because the boundaries of the segmented instance on the panorama the boundaries are not clear. The boundaries are not following exactly the object. How the object should be. And if we were to project the information from the panorama on the 3D mesh, then we would see that it is actually going to start leaking all around in other surfaces where it shouldn't be, as you can see on the slide. And another reason is not only that the instance segmentation mask might not be 100% correct, there are also issues of registration of the camera under 3D mesh, or because the reconstruction of the objects is not perfect. That leads to this leaking of semantic information in 3D space. However, given the way that this data was collected, we see that the same object is actually visible from multiple cameras, from multiple viewpoints. And we can leverage that in order to fix these errors that we have right now from leaking semantic information on other surfaces. And in order to do that, we build another weighted voting scheme that takes into account the distance of each surface from the camera, the instance segmentation, and we do this. And as a result, we get what you see on the right side of the slide. Now we found all the objects in the 3D scene graph. So we are now going to compute attributes and relationships, and we do that in a mostly analytical way and learning wherever that is possible. There are, of course, cases where the learning methods that exist out there, because we use off-the-shelf methods, were not providing good results. So in some of those attributes, we actually had to manually annotate them ourselves. In terms of relationships, we provide information on modal masks. So what are the occluded and visible parts of an object given a camera, the spatial order of an object, if it's in front or behind others in the scene, as well as the relative volume. So these are just some examples of relationships that you can compute. Here is, I'm not sure if you can see that very clearly over Zoom, because it usually has some hiccups, but here are the results of the instance segmentation. This is how the space looks like, and this is the information that each node in this scene graph has. So we can see here all the attributes for all those objects, and here are some of the relationships that can happen between different instances, such as spatial order or occlusion, if the table is occluding the refrigerator, for example, as well as relative volume, whether the oven and the microwave, which is larger than the other one. And once we collect all this data, we want to make sure that it's as accurate as possible. So we use a user in the loop verification step, where we take each of the resulted images from the automated part, and we crowdsource this verification step. We first verify the label. So given an image where the found object, the detected object is in the center of the frame, we verify whether it's the correct label or not. And if it's correct, then we look at the mask. And if the segmentation mask is correct, then we're going to keep it on the side. That is going to go into a second step, where given a larger image, where now we don't necessarily frame each object in the center of the image, then we're going to look if all instances of an object category are masked or not, and we're going to add any missing objects. So in that, with this, we can make sure that we are fixing any issues from before, and we are adding any objects that were missed from the detectors. Now, how do we evaluate this method? We evaluate two things. First of all, how is the performance of the mask or CNN improved given these two robustification mechanisms, and as well as if the user in the loop is faster in comparison to doing manually everything from scratch. For the sake of time, I'm going to just quickly discuss about the quantitative results, where we have the masker CNN, first of all, both in 2D and 3D space. And we see that it performs a certain amount. And then we see that by doing the framing step, which is the first of the two robustification mechanisms, we have a pretty good increase in the results. And when we also do the second step, which is that of multi-view consistency, we see that the average precision is and the average recall are both increased even more in both modalities, both in the 2D and the 3D space. We see a similar behavior, even if we do not only use mask or CNN, but one that has less accuracy reported on the COCO data set, as for example, BlitzNet, and we see this similar kind of performance. Finally, when we see whether it's actually doing any faster or we should just do everything manually, we see that it's about 7 times faster than doing everything from scratch, annotating both 2D and 3D modalities. So in that sense, there is some value in doing this step of automation. And we also saw that the automated results without the user verification step are of practical quality. And specifically, we performed 3 experiments on spatial order, relative volume, and a modal mask prediction, where we predicted both the occluded and the visible part of an object. And the results that we got were very promising. We can also use this information in order to get, for example, co-occurrences of objects. In this case, what is the nearest object of microwave usually in the house? And we see that in most cases it's the oven, which makes a lot of sense, and then the sink. And also for any other object category you might have in the data set or in your 3D scene graph. So concluding, I would like to discuss how we can go forward from here. So we have this 3D scene graph, but how does it connect to this physical world and digital representation and the dynamic environments that we would essentially like to have in order to establish this seamless interaction between the physical world and the digital space. Well, so far I've described just a static space where we only have the building and nothing else, but buildings are made for humans, and humans interact with those spaces. So that means that we should be introducing into our semantic understanding and our 3D singgraphs and any kind of higher level understanding of our spaces, the aspect of time and the aspect of humans, how we're interacting with space and how spaces changes over time. With that in mind, we should also think about a little bit more about the aspect of humans and how humans interact with not only the space and the objects around them, but also with the machines, and in specific how we can use them in order to increase the accuracy and improve the accuracy of our methods, be that for semantic understanding or for even localizations or localization of camera. With that, I would like to thank my collaborators that helped me make this work happen. And I'd be happy to take any questions.
Thank you, Iro, for this great talk. If there are any questions from the audience, please use the Q&A tool that is provided by Zoom. Just post them there and we will relay them to Iro. So maybe while people have the chance to, while people are starting to write down questions, I have a couple of them. So when you talked about the single panorama case, you said there's errors in the camera poses, in the geometry and so on and so on. And your voting scheme, but the voting scheme still assumes that the camera poses are halfway meaningful because you're just doing voting in 3D, 2D, right? Or do you also optimize over the camera poses between the panoramas?
Right. We consider the poses as we do not update any camera location. We just take it for granted, but we are trying to make sure that we do not mitigate errors that come out of out of the 3D reconstruction of the space, that we do not mitigate them into semantic understanding that we are doing later on.
Do you have an idea of how costly it would be to optimize over all quantities, semantics, 3D geometry, camera poses? Does that quickly become infeasible, or?
I would think that it does become, like, we started thinking of how we could also introduce maybe more attributes, for example, in just even this, in order to do the instance segmentation. So in order to identify and how you can link views one with the other and which objects you see in which image, because you do not have that information since you are not, you really do not have that. Then it just becomes a little bit intractable after a certain point, too much information and without necessarily being obvious the benefit of using all these.
Yeah, that makes sense. So would it help to, so one interesting and application for those scene graphs is, as you said, autonomous agents, right? Robots navigating through this. Do you think there's a benefit from observing like where robots or agents walk, drive, and feed that back into the construction of the scene graphs? Like having this information, or do you get this essentially for free through the semantic segmentation?
Right, so ideally it would be the second, if your algorithm is able to perform correctly. So I always envisioned using 3D scene graph in order to help tasks that have to do with, let's say, navigation inside a space, because robots do not learn that well when they're doing navigation on the metric space. They would learn better on a semantic kind of layer instead. However, what you're saying is a very good point, because what I am saying assumes that you already have the 3D scene graph of the space. But what if you're building it on the go? in that sense, then you would definitely would like to rely on building it on the fly using the data from the agent. And that brings up very interesting questions in terms of how does it change and how can you dynamically update the graph in order to fix any errors or include new observations.
Yeah. In that regard, do you know how much human intervention was actually necessary for your scene graphs? Because you said you ask humans to double check.
Yes. Well, I mean, we mostly evaluated it in terms of time. And if we consider that fully automatic takes 0 human time, right, then a manual verification took another 3 hours to complete for one model when we had 2 users verifying the results. And the accuracy, the average precision really improved by around 0.4 to 0.97, almost 100% accuracy. We still were not able to reach 100%, but you know, it's a big it's a big topic, and I don't think we can. It's out of the scope of this Q&A, I think.
Yes, definitely. But I mean, it's what excites me about it is that there are so many possibilities once you have this type of semantic representation. So, I mean, robotics, localization, and I think the exciting part is interaction with the scene. Yes. Like this is what a scene graph enables, right? Exactly. And maybe one question there: do you actually just label raw like static geometry, or do you actually also like cut out potential dynamic things? So is on the theory level, is it the static scene or is it like an object-oriented representation?
That is a very good question. As of now, it's just the surfaces. We just label the surfaces on the mesh. We are planning on being able to add object-oriented bounding boxes around or around those instances that could help in at least aligning shapes, objects from ShapeNet, for example, and identifying which parts might be movable or not. Right now, we don't have that. If anybody wants to do it.
Yeah, but it sounds exciting. I currently don't see any questions from the audience. Does one of the other panelists have any questions that they would like to ask? Now would be the time. I mean, I could go on for like probably half an hour asking questions because I think this is really exciting work. But yeah, if there's no more questions, then I will not continue rambling on, but let's thank Iro again. Thank you very much.
Thank you for having me. Have a great workshop ahead.
Thank you very much. Our pleasure, and good night. Thanks for staying up so late.
Absolutely. Bye.
Bye.